Hi, this is Professor Fernandez, and in this video, we're going to work out some examples on power series representations. And this video comes from, these examples are going to come from lesson 12. And the notes for that lesson are available on the website. Also, you'll find these other things on there as well. So power series representations, this is a topic that we've gotten to after investigating the lesson before this, lesson 11. In that lesson, how we can get power series to converge, right? So for certain x values, a power series converges. And then the idea is, if it converges, then what does it converge to? Well, so then maybe we can, for example, if we have a power series x minus c to the n equals 0 to infinity, and we know that, I don't know, for x equals 7, it converges to a number like 10. That number is going to be unique because it's the sum of an infinite series. So maybe can we create a function, right, that says that f of 7 equals 10, like f of x, right? So can we, in other words, consider the entire power series as a function of x? The answer is yes, we can do that, as long as whatever x value we're looking at for the input yields a convergent infinite series, and it converges to some sum. As I was assuming here 10, then we'll know that f of whatever that x value is, like 7 equals 10. So in other words, we can take power series that we know convergent in the interval of convergence 4. And for all the x values in there, the power series defines a function. So that's pretty cool. So we have already some information in the course that we've been carrying along about certain power series that we know the actual function formula for. The most amusing and really incredible one is this one. It's amusing in a way because it's really just the geometric series formula in disguise. We've talked about that in previous videos. It's really incredible because this is a power series, right? Compare this to an, x minus c to the n, summing from 0 to infinity. C is 0, and all the ANs are 1. So this is a very, very special power series. And it happens to be equal to this function. So this is a function f of x. We just talked about this also being a function within its interval of convergence, which is over here. And the fact that the two of them are equal is really just like mind-blowing, right? This is an infinite series. This is a function you could graph. You probably studied in pre-calculus, and here we are saying that these two very, very different things are equal. So this result is the one that we are going to use over and over again in the course as we start investigating this connection between power series and functions. And it's also the one that we're going to use for this example. So I'm going to just move it around, kind of out of the way, because we're going to make use of it to solve these two examples. So let's get to the examples. They say find a power series representation for the functions below and determine its intervals of convergence. You might also see this question asked a little differently. It might say expand the function in a power series centered around 0 or something, right? That word expand, you might see that also. Okay, so what are we going to do? We're going to, first of all, zoom in here a little bit. We're going to take a look at this function. This is a function, right? And then we're going to try to make it look like this function, or vice versa. Start over here and make it look like that, right? You can go either way. Why? Because of what I said earlier. We already know that this function equals this specific power series for this interval of convergence. So if we can take this function and make it look like that somehow, then you can see all these things I just said will kick in, and we will have our power series representation along with the interval of convergence. All right, so I'm going to write, therefore, the function over here, 1 over 1 minus x, 1 over 1 minus x, and I just wanted to write it next to or really below this function so we can kind of talk through how we might get f of x to look like that. And really, here's what you do. So you take this. It helps to have seen this once, and then you kind of can see how it's going to go. And notice the differences and the similarities. First of all, we have a quotient, right? 1 divided by something, or something divided by something. Same thing over here, so we don't have to do anything there. The numerator is also 1, don't have to do anything there. The denominator starts with 1, don't have to do anything there. So the only difference is this plus x cubed. It is in the place of negative x. So I can then take this and write 1 minus negative x cubed. And you can see where I'm kind of heading with this, because I'm now going to consider all of this as the new quote-unquote x. So I'm going to write out the power series for 1 over 1 minus x, right? Here it is down here. It's x to the n. But that x, right, this one right here, is the one that's over here. Now what I've done is I've replaced this x with negative x cubed. So therefore I'm going to go over here and I'm going to replace that x with negative x cubed. Okay? So I did it a certain way to try to introduce this in a way that hopefully demystifies how we are getting one function to look like another, and then using the power series representation that we already know. But I do want to do this one more time in a different way, just again to give you options, right? So another way to do it is you start off with the power series that we have, right? There it is. And then what you do is you go in here and you say, oh, let me plug in negative x cubed, right? So let's call this, I don't know, h of x equals that. So now let me plug in negative x cubed wherever I see an x. So that's 1 over 1 minus negative x cubed. It also gets plugged in over there because that has an x, negative x cubed. Okay, and notice that then we've done the same exact thing, right? Here, this term is the same as that term, and then this power series is the same as that one. And then also notice that, this thing is equal to 1 over 1 plus x cubed. That's the function that we're trying to find a power series representation for. So I've done this now 2 different ways, right? Number 1, which was more about starting with the function that we know has a power series representation, and then comparing it to the function we're trying to find a power series representation for, and then going that route. The other way over here is starting with the 1 over 1 minus x form, and then substituting whatever I need to substitute, in this case minus x cubed, to get it to look like the function that I'd like to find a power series for, and then again carrying that substitution through to the power series for 1 over 1 minus x. Whichever way you do it, right? I'm just going to remove the clutter here. Whichever way you do it, it doesn't really matter. You are going to end up with the same result. So whichever one of those explanations, hopefully at least one of them, makes sense to you, let's go with that one. And if not, send me leave a comment below, and I'm happy to chat with you. So what do we do now? So we keep going, right? So we have this minus x cubed to the n. So first of all, minus 1 to the n, right? That comes from raising minus 1 here to the n. And then we have x cubed to the n, and then we just keep going here. So minus 1 to the n, x to the 3n, right? These exponents multiply. This is the power series for 1 over 1 plus x cubed, okay? So it really is just that straightforward in the sense of, again, if you, whichever one of these 2 ways we talked about, after you, substitute whatever you're going to substitute into the power series for x to the n, then you just kind of simplify it, and that is your power series. What about the second part of the question, right? So we found the power series representation. How about the determine its interval of convergence? Okay, so we go back to what we had here. So now we're going to look at the same results through slightly different lens. This is the function, which is equal to this power series, on this interval of convergence. And this x is the same x here, same x here. So when we're here, we're substituting minus x cubed into this x, right? We also put it in here because it was this x. And then we're going to do the same thing. We're going to put it in here. So I'm going to go over here and write next to this power series, absolute value less than 1. And this x down here, I'm going to replace it with the x that I've been replacing here, minus x cubed. Okay, so this is the new interval of convergence. Now, most of the time you don't want to leave it like that, right? You would want to actually simplify it a little bit. So let's work that out. So first of all, absolute value of negative x cubed, it's the same as absolute value of x cubed. And then the absolute value of x cubed is absolute value of x cubed. And then I take the cube root of everything, and everything is non-negative. So I just get the cube root of 1, which is 1. So it turns out that the interval of convergence is also the absolute value of x less than 1 that we had before. But if I had to then write out the full solution to erase some of the clutter and leave only what is part of the solution, we would say, okay, so this function equals this power series on this interval of convergence, right? So that would be the full solution. And again, we based all of that information on manipulating the power series for 1 over 1 minus x, which we have information for in terms of its interval of convergence, in terms of what it equals, in terms of the power series itself. Great, so we did part A. So now let's go back and take a look at part B. And this will be a little faster now, partly because we know what we're doing, and also partly because if we look at the function here, g of x, it's actually 2x squared times 1 over 1 plus x cubed. So 1 over 1 plus x cubed is the same function that we just finished working on. So this new function g of x is just 2x squared multiplied by that. Okay, so I'm going to take this result, which is for part A, move it over here. This was for part A. Let's label that. This is part A. And then part B, I'm going to say, all right, so this function is just 2x squared times this whole thing, right? So first of all, 1 over 1 plus x cubed is this. So I'm just going to put that in here. So what am I doing here? I am literally substituting 1 over 1 plus x cubed for the power series that we know it's equal to from part A. And then, comma, absolute value of x less than 1, right? When you substitute this rational function for this power series, we know, we just showed in part A, you can only do that so long as absolute value of x is less than 1. So you might wonder, what about this 2x squared? You know, am I done? Is that the end of the problem? And yes and no, right? It would be nice if we wrote this as a single, a single power series. Or in other words, not like a function of x times a power series. The way you do that, really, the number can stay outside, it can come inside. I'll just bring it inside. There's the 2. And then x squared, you multiply inside here. So 2 minus 1 to the n, x to the 3n times x squared. Then you have the same base. So we're going to add the exponents. Sum from 0 to infinity, x to the 3n plus 2. You can see now that this is a cleaner way of expressing the power series, and it also gives us all the information that we were asked for and that we need. This is the power series that is equal to 2x squared, the function, over 1 plus x cubed. There we go. And we know its interval of convergence. Notice that the interval of convergence did not change. So let's talk about that real quick, right? Why didn't it change? Well, the way we have done this, which is the way to do it, is we took 2x squared and we multiplied it by the power series for 1 over 1 plus x cubed. That is what brought up the interval of convergence, right? So we know from part A that the only way that this is equal to this is if absolute value of x is less than 1. That's literally how that restriction comes about. So it's not like we need to multiply 2x squared by this. That's not the way those two things work out, right? What we need to do then, in some cases you might need to do this, is think about, does this algebraic operation add or subtract anything to the interval of convergence, right? Does it further restrict the x values for which the power series converges, or does it not? In this case, it doesn't. We're just multiplying by 2x squared. And once we make the substitution that this equals that, and therefore we're on this interval for the x values, that also ends up restricting the x's in 2x squared that we can multiply by, right? So that's another reason why I wanted to slide everything in here, because now this entire function equals this power series on this specific interval, right? So for example, we do not get the case that I can find g of, I don't know, 34. Okay, so g of 34 is not equal to plugging in 34 in here, because 34 is not in this interval. Okay, even though I can certainly calculate 2 times 34 squared. All right, so make sure again that you understand that distinction. Once you have your original function, and once you substitute in a power series, you are now restricting the set of x values that you can use for whatever other additional calculations or manipulations you're going to do, like multiplying by 2x squared. Okay, so I'm going to zoom out here. A lot of arrows and things going in different places, but I do encourage you to go back to the video and review some of what we did. Keep in mind this main result that we were using, right, which again I mentioned is the geometric series result in disguise. This is going to come up, like I said earlier in the video, over and over again, right? So you can see this function was a variant of that one. But what about this, or what about this, or what about that? You can see these are all variants. Here are 5 variants of effectively this, right? And you can get to them in different ways. For this one, we're thinking of this as 1 minus negative x. So you take negative x, put it in there. Over here, this is x times 1 over 1 minus negative x. So the result from this one times x, right? For this one, it's 1 over 1 minus x squared. So we take x squared, we put it in for x here and here. So you can see kind of how this game goes, that there are going to be a lot of rational functions that are going to look vaguely like 1 over 1 minus x, and through some combination of multiplication, addition, substitution, right, division, you will end up with a power series that looks vaguely like that one. Okay, thanks for watching.